Dear classmates, welcome back to the VLSI testing class. This chapter is fault simulation. This is our course roadmap. Now that we have basic knowledge about logic simulation and we know some basic concept about fault modeling, now we enter an important topic, fault simulation. Here is a motivating problem. Suppose we design this circuit and we decide to apply three patterns 0, 1, 0, 0, 0, 1 and 1, 0, 0 to this circuit. And your manager asks you, what's the fault coverage of your test set? How are you going to answer this question? To answer this question, we will need fault simulation. So, why am I learning this chapter? A fault simulator can help you on three things. A fault simulator can help you to determine fault coverage. Second, a fault simulator can guide ATPG to determine which fault has not been detected yet. And the third, fault simulator can help us to diagnose failed chip. Here we have a famous quotation from Victor Hugo. He said that one sees qualities at a distance and the defects at close range. This is an interesting quotation. In real life, we should look at other people's qualities instead of their defects. However, for circuit testing, a fault simulator should check each defect very closely. In the fault simulation chapter, we will first do a short introduction, followed by many fault simulation techniques. We will also introduce alternatives to fault simulation. Then we will discuss some issues of fault simulation. Then we conclude this chapter. So what is a fault simulator? We show a very similar figure in the logic simulation chapter. In a fault simulator, we are given a set of input stimuli, which is our test patterns, and we are given circuit models as well as the fault models. This is different from what we had in logic simulation. And the fault simulator will give us the good circuit response as well as the faulty circuit response, so that we can know which fault has been detected and which fault has not been detected, and we can calculate the fault coverage. So in this figure, we can see the difference between logic simulator and the fault simulator. So what are the applications of fault simulation? First of all, we can evaluate the quality of our test set. This is what we call fault grading. With fault grading, we can determine the fault coverage of a test set. This is like grading an exam. And the second application is automatic test pattern generation, ATPG. Fault simulator can identify which fault has been detected and which fault has not been detected. So ATPG can continue to work on those undetected faults. The third application is diagnosis. The fault simulation can generate a fault dictionary to find the culprit fault response for the failure. We will see this in more detail in the diagnosis chapter. To sum up, fault simulation is a very useful tool. It can be used as a standalone tool for fault grading, or it can also be used as an embedded tool for ATPG and diagnosis. This is a typical flow for ATPG. After we pick a target fault, we try to generate a test pattern for it. Then we run fault simulation to determine which fault has been detected. Then we perform a fault dropping. Fault dropping means that we remove the detected fault from the fault list so that we can prevent repeated test generation for the detected fault. The reason is that a fault can be dropped as long as it is detected once. Please note that fault dropping is not used for diagnosis. We will see the reason in the diagnosis chapter. And then, if there is any untried fault, we will keep in this loop until all the fault has been tried. As you can see, fault simulation is the core engine for ATPG, so it is a very important technique. In this chapter, we will show 6 different fault simulation techniques. We will start from the simplest fault simulation technique, the serial fault simulation. A simple idea to implement a fault simulator is to first run a fault-free logic simulation, store the good output, and for every fault, we modify the good circuit. This is what we call fault injection, to obtain a faulty circuit, and we run logic simulation on the faulty circuit. We compare the faulty output with the stored good output. If they are different, then the fault is detected. The advantage of serial fault simulation is that it's very easy to implement. It's based on a regular fault simulator with some small modifications in the circuit. And we are able to simulate many fault models such as stuck-up fault, delay fault, bridging fault, you name it. The disadvantage of the serial fault simulation is that it's very slow. Here is an example to illustrate the idea of serial fault simulation. Consider only fault F and the fault G. Fault F is A stuck at 1 fault. Fault G is J stuck at 0 fault. Given 3 test patterns, pattern P1, P2, and P3. We run the good simulation and the outputs are 1, 1, 0. We store the output. And we modify the circuit and run a fault simulation for fault F. We can detect fault F because the faulty output is not the same as the good output. Assume there is no fault dropping. We can still detect fault F for the second pattern, but we cannot detect fault F on the third pattern. And then we pick fault G. We cannot detect fault G by the first pattern, neither the second pattern, but we can detect fault G by the third pattern. So here we show a serial fault simulation flow. Given the big F, which is a collapsed fault list, we run fault-free simulation for all the patterns and we store the good outputs. Then we pick the next fault, small f, from the fault list. We start from the beginning of the test set. We pick a pattern P, run the fault simulation for pattern P. If the output are the same, then we pick the next pattern. We continue this loop until the end of the pattern or the 4F is detected. When 4F is detected, we drop it from the fault list. This is what we call a fault dropping. After that, we pick the next fault. As you can see in this flow chart, we have two loops. The inner loop is a loop of pattern. The outer loop is a loop of fault. We can speed up fault simulation by fault dropping. Here, it's a quiz of our motivating problem. Given 3 test patterns and consider all the 18 faults, please use the serial fault simulation to determine the fault coverage. For example, given the first fault A1, when we inject A stuck at 1 fault, we know that it's detected by pattern P1. If we inject fault A stuck at 0, it's not detected by any pattern. So now please pause the video and continue to work on the other 16 faults. Okay, now back to the video. Here are our answers. Have you got them all correctly? Looking at this table, we can see that 7 faults are not detected by any pattern, and 11 faults are detected. So our fault coverage is 11 over 18. As you can see, this is a pretty slow process. So what's the complexity of fault simulation? The complexity of fault simulation is big F, which represent the number of faults times number of test patterns and the number of gates. So it's more complicated than logic simulation by a factor of F. If you remember, logic simulation complexity is only O G times P. So compare with logic simulation, fault simulation is more complicated computationally. On the other hand, ATPG is NP complete, so in the worst case, it can be exponential. So compare with ATPG, fault simulation is easier. So we can use fault simulation to guide ATPG to determine which fault has been detected. In summary, ATPG is the most difficult computationally, and fault simulation and logic simulation is the simplest computationally. In summary, in this video, we have introduced fault simulation. A fault simulator produces faulty circuit output. It can be used for fault grading or ATPG or diagnosis. Fault simulation is polynomial time, which is O P times G times F. We have shown you the simplest fault simulation idea, serial fault simulation, which simulates one fault by one fault at a time. At the end of this video, we have a FFT for you to think about. In our fault simulation flowchart, we see that there is an inner loop of pattern and the outer loop of fault. Can we just swap the inner loop with the outer loop? If we do the fault first, in this way, we can drop the fault faster. Is this a good idea? Please think about it. Thank you for watching.